All right, back at it. A train car traveling on a straight track at 40 miles per hour. Speeder speeds up as she skis downhill, which is a net force greater. So this one, it really just comes back to Newton's second law and what it says that the net force or the sum of the forces is equal to mass times acceleration. And then you're really asking yourself between these two situations, which one has a greater acceleration? With the train cars, it's traveling at a constant 40 miles per hour. So a constant velocity. If you have a constant velocity, then A is 0. So there is no acceleration, so the net force is 0 acting on the train car. However, if you have a skier that's speeding up, then that definitely implies that there is an acceleration. If right, you might want to try and argue with me, like if you have this skier, it's going down a hill, and if you were to find down is negative, then maybe this is a negative acceleration, and then you're comparing 0 versus a negative number, then obviously 0 is greater than that. But I think that's kind of taking it a little too far. If you have a speeder, they're speeding up, then we have an acceleration. So the net force is greater on the skier as opposed to the trainer, or both of them. Okay, here we go. 10-year-old Sarah stands on a skateboard. Her older brother Jack starts pushing her backward and she starts speeding up. We're interested in comparing the force of Jack on Sarah compared to the force of Sarah on Jack. So take a moment, pause the video, think about that, decide what is relevant, and then come on back when you're ready. Okay, so for this one, I just kind of want to give you the answers straight out. The force of Jack on Sarah is equal to the force of Sarah on Jack. This is just a straight up Newton's third law pair problem. Newton's third law pair. Okay, and this is no different than the example that I give over and over again. If I'm touching the wall is touching me, and those two forces have to be equal and opposite to one another. So that is what's happening here. Jack is pushing on Sarah, and as a result, Sarah is pushing back on Jack. The fact that Sarah is speeding up has nothing to do with the actual contact between Jack and Sarah, but has something to do with the relative frictional forces acting between the wheels on the skateboard and the frictional force between Jack's shoes and the floor. Okay, one more ABCD question. So you have this relatively complicated diagram. You've got two boxes that are stacked on one another. The top one is tethered by a string to a wall. There appears to be a frictional force between the two blocks themselves. The bottom box is being pulled off to the right by a force of 20 newtons. However, there is no friction between the box B and the surface. Okay, and the question asks, what pair of forces is an action-reaction pair out of the four provided? So take a moment, read all of your options, pause the video so you have time, and we'll see where you're at. Okay, so things to keep in mind when you're talking about these action-reaction pairs or third law pairs, however you want to call them, is there are very specific conditions. The first one is that they're the same type. They have to be the same type of force. So I think actually with that one condition, we get rid of lots of options. In A, you have a tension force versus a friction force. Those are not the same type, so A is out. B is a normal force and a weight force. Those are not the same type of force, so B is out. C is the same thing, a normal with a weight. They are not Newton third law pairs. But the last one is, or at least it has the same type. They're both frictional forces. Okay, the other conditions for the third law pair, they act in opposite directions. Okay, so if we're looking down our last option, it says the frictional force acting on A. Okay, so I'm going to erase my frictional marks. The frictional force acting on A versus the friction force acting on B. So the frictional force acting on B is kind of the easier one to think about. It's opposing the motion going to the right, so the frictional force on A has to be going to the left. If all of block B is trying to move to the right, then the frictional force on A would have to be trying to go to the right, which is counteracting the tension force from the string. So those two arrows are going in opposite directions. The third condition is the two forces act on different objects. Okay, and that's clearly stated because it's stating A on A versus on B, so those are two different objects. And the last condition, which I don't think is necessarily possible to explicitly prove with this picture, is they need to be the same value. So they'll both be like 10 newtons or 15 newtons or whatever the actual value is. So in this problem, though, the Newton third law pair or action-reaction pairs are the frictional forces acting between A and B, the one that's acting on A versus the one acting on B. All right, I think we can do one more before we run out of time here. So our first maybe full example, we have a 100 kilogram block with a weight, which I'm going to put in quotes, of 980 newtons hangs on a rope. Find the tension in the rope if it moves upward with a constant velocity of 3 meters per second. So first off, we definitely need a picture. So we have a rope, and on it we have a block, and presumably this rope is attached to some kind of ceiling. This is a 100 kilogram block. If I want to draw a force diagram, I need to do it for the block itself. So the only thing touching the block is a tension force. So I have an F tension pulling up. It's the only thing touching it. So then we can remind ourselves that we more than likely have the Earth down here. And so we also need to have an F grav force as well. Okay, if we want to talk about relative lengths of these two things, we need to make sure that we take into account information provided in the problem. It's telling us that it's the rope is traveling upward with a constant velocity, so maybe it's not a ceiling, maybe there's like a pulley system, sorry. But it's a constant velocity. If it's a constant velocity, then there is no acceleration. If there is no acceleration, then these forces must balance one another. So we can be very explicit about it. We can go and say, hey, I'm going to sum my forces, and that equals to mass times acceleration. It means that I'll have the F tension pulling in the upward direction, so that's positive. I will then have my F grav, which is pulling down in the negative direction. So I have F tension minus F grav. And right, we just decided that A was 0, so the right-hand side is equal to 0. And then we actually have this explicit mathematical statement that the F tension has to be equal to the F grav. We can then remind ourselves that F grav is the weight of the box. And so the F tension is equal to 980 newtons. Okay, so take note of the steps here. We drew a picture, we drew a force diagram, we assessed information from our problem, we summed our forces, and we solved with what we knew. And those are the general steps that you should always follow with these force problems. Picture, force diagram, information from the problem, sum your forces, solve for the thing you're looking for. All right, I'm going to stop this one and do one more video for the last two problems we have, and then you'll just have to wait until I come back on Monday for more fun forces.